So here's problem number 10. Someone pointed out that it's not done in the video. So here's some introductory remarks at the top, and then a picture which isn't very big on this screen of the hydrogen atom, and then a series of questions you have to answer. So the first thing you need to understand is that a hydrogen atom is a proton and an electron, and that's it. And the electron orbits the proton. And so we know from this week that when two point charges are near each other, there's a potential energy. Which is equal to K Q1 Q2 over R, not R squared, for the energy, right? So that's the electric potential energy we can calculate what the electric potential is of the proton and the electron. And you'll notice that the proton and electron are positive and negative, so there's an attractive force. So the potential energy is going to be negative. And if you look down at the first question, the total energy of the hydrogen atom must be negative. And the way we think of a negative energy is if you have two charges that are under the influence of each other, there's either, if we put a positive charge here, right, it has a positive energy because if I release this charge, it goes away. If I release the electron from rest, it's going to fall this way, and it's going to drop in energy and gain kinetic energy. So the zero energy for electric potential energy, it's at infinity where the energy is zero. Only if two charges are far apart is the energy considered to be zero because they're not influencing each other. So the way to think of the negative energy of the electron in a hydrogen atom is the amount of energy it takes to remove it from the atom. And if you remove an electron from an atom, you've ionized the hydrogen atom. This is kind of a combination of chemistry and physics. And the amount of energy it takes to get the electron out of the atom, out of the influence of the proton far away, is the ionization energy. And that would simply be this, right? You would put in the K, you put in the positive 1.6 times 10 to the minus 19 coulombs, negative 1.6 times 10 to the minus 19 coulombs, and the distance between them, which is given, the radius of the hydrogen atom, and that gives you the potential energy, and that's negative. So we'll calculate it later, but just let's say it's a negative 10. That's the amount of energy it would take to ionize the hydrogen atom if the electron were stationary, but it's moving, right? So it has kinetic energy. So it already has some of this 10 units of energy that we need to remove it. So to find out the ionization energy, we need to calculate the electric potential energy, which is going to be negative, and add to it the kinetic energy that's already in the electron as it orbits the hydrogen atom. And so to get the kinetic energy, we have to know the electron's velocity. We know its mass, right? It's given, but we got to find the velocity. And the velocity we find by going back to first semester physics, and we studied when we talked about planets like the moon orbiting the sun. So let me pause. I'm talking too fast. The moon orbiting the Earth. Whoops. Here's the Earth. Here's the moon. And it goes around, right? And there's only one speed the moon can go around in. If the moon goes slower, it's going to fall to the Earth. And if it goes faster, it's going to go away from the Earth. So there's one unique velocity called the orbital velocity that's determined by the magnetic force, the gravitational force, and the distance. So the same is true of the electron. Let's go to the electron and the proton. So an electron in a hydrogen atom, whether it's moving or stationary, is subject to a force. That's Coulomb's law. So I've written down what the force is. It's K Q1 Q2 over R squared, where R is the radius of the atom. And that has to be equal to the mass times the acceleration, right? And if it were stationary, the electron would just accelerate toward the proton like that. But if it's moving at the right speed, the centripetal acceleration will exactly match the force, and it will be in stable orbit. So from last semester, you may remember, and if you don't, I'll remind you, that an object moving at a constant velocity in a circle has an acceleration of v squared over r, where r is the radius of the circle. So that's the same r as the radius of the hydrogen atom. And so notice that I have this is equal to this. And if I multiply both sides by r, this becomes cancels one of that r squared. And so I'm left with mv squared. Can you see this? I'm left with mv squared is equal to kq1 q2 over r. So if I multiply both sides by 1/2, this is a trick you might not see otherwise, multiply by 1/2, I have 1/2 mv squared. So an electron in a stable orbit going around the hydrogen atom will have a kinetic energy of 1/2 k q1 q2 over r squared. Now let's go back to what we said earlier. The electric potential energy is K Q1 Q2 over R. And so this is the same thing. Notice, this is half of it. So what this is telling us, remember, this is a negative number, and I made up a number of 10. If this were negative 10, this number here, the kinetic energy is half of it, so this would be 5. So let me erase what we have and write it out again. So as we said a couple times, the electric potential energy is kq1 q2 over r. Now remember, q1 is the proton, a positive 1.6 times 10 to the minus 19, and q2 is a negative 1.6. And so we could write this as negative k e squared, where e is the 1.6 times 10 to the minus 19 over r. And similarly, the kinetic energy, which we found previously, is 1/2 this amount. So it's 1/2 k q1 q2 over r, or 1/2 k e squared, where e is the 1.6 times 10 to the minus 19 coulombs over r. And this is a positive number. Kinetic energy is always positive. So that means that the total energy is going to be the sum of those two. One is negative and one is positive. And the total energy ends up being negative. And since this is K, negative K, E squared over R, and this is positive 1/2 K E squared over R. The math is so simple you might get confused. The total energy ends up being the ionization energy, right? The total energy ends up being negative 1/2 when I add these two numbers. Negative 1/2 K E squared over R. And so the ionization energy, that's the total energy. The ionization energy has to be this amount of energy. And if you put all those numbers in standard units, you'll get units of joules. But if you want to convert the joules to electron volts, then you use the conversion factor that's given above. Let me see if I can. All right, there's your conversion factor. Oops. And that's what you need to answer all those questions. I hope that helps.